This question is about orbital time period and the relationship between orbital radius and the time period of the orbit. So if we look at this, we can see we've got some graphs for t against r, a variety of functions of t against r, and we're asked to indicate which one we think is correct. So just to draw your attention to one other thing, it might catch you out. None of these graphs, so all of these graphs appear to go through the origin. So they're all equivalent in that sense. So we're not looking for one that doesn't go through the origin, and I'll explain that in a second. So we have the relationship we're looking for, which is a standard set of calculations, which ends up with us demonstrating Kepler's law. So GMM over r squared, or you could have GM1 m2 time over r squared. That's the gravitational force that provides the centripetal force that allows the mass m to move with a velocity v in a circular orbit r. They cancel, the mass cancels, so the mass of the object in orbit cancels, and we end up with gm over r equals v squared. But it's moving in a circle, so we can get an expression for v in terms of the orbital period and in terms of the orbital radius. And this is a standard set of calculations, derivations to end up with this. So v, which you may have seen at GCSE, it's the circumference of the circle divided by the orbital period. So v is the circumference of the circle divided by the orbital period. If I put that into this equation, I end up with that gm over r equals 4 pi squared over t squared. I can rearrange, so I've got an expression in terms of 2 pi r squared. So I can rearrange this, so I get an expression in terms of t and r, and I end up with t squared is equal to 4 pi squared over gm is equal to r cubed. So the relationship is that t squared is proportional to r cubed. If I was to have this in terms of just t, I can graph A. So just in terms of t, so then t becomes y. So I'll square root both sides. If I square root both sides and just consider this as a constant, then it will go through the origin, but you end up with t is equal to some constant, and then it's r to the 3 halves. Now it's 3 halves, not 2/3, so that first graph would not give you a straight line, so it can't be A. If we then look at B, so we can use this relationship I've got here. So t is some constant r to the 3 halves. So t is some constant r to the 3 halves, and then I take logs of just t. I can't really take logs of just t in this relationship because that doesn't make any. So I can express it in terms of r, but I can't take logs of both sides, so it can't be b. Then if I look at c, if I take logs of both sides, I get log of t is the log of some constant plus the log of r to the 3 halves, and that 3 halves can come down to the front. So that would be a straight line. Doesn't go through the origin because we've got this log k, but this is the only one that will give us a straight line. D doesn't work for the same reasons that B doesn't. So that might put you off unless you've seen it before. So it's not expecting us to realize that it wouldn't go through the origin, and it doesn't explicitly say it's the origin, but it's the only one that would give us a straight line, so it must be C.